So we just found the area bounded by the inner loop of this polar curve. So maybe another question might be, how can we find the area that's in the outer loop, but not in the inner loop? All right, so that's going to be everything that I didn't shade here, right? So all of the stuff that's inside the big loop, but then outside of this. So all of this stuff right here. And that's messy, so I'll erase that, but that's what we're looking for. All right, so one thing that people are going to try here, and it's going to be wrong, is they're going to say, okay, well, I know that the curve gets traced when theta goes from 0 to 2 pi. That part is correct. So I guess I'll just integrate from 0 to 2 pi, find the area of the entire thing, and then subtract this area. Well, that's going to be wrong, and I'll leave you to figure out what you actually do get when you integrate, in this particular case, what do we get when we integrate 1/2 0 to 2 pi of r squared d theta. It's true that 0 to 2 pi does trace out this curve. It goes here, whoops, no, that's not how it goes. It goes like that, yeah. But it's not going to give us the area of the curve, the total area bounded by the curve. So I'll let you figure out what represents what. Represents what? And what we'll do is actually do the actual problem. So if we're going to try to find, it's a good strategy, right? It's a good strategy to try to find the area bounded by either of the loops and then subtracting the answer that we got on the last problem. So that's what we are going to do. So when we do that, we're going to say, well, we're going to start at this point and find that area that goes all the way around to here, and then that's the top half, and then we also have the bottom half, right? And we're going to stop right there. Notice we're not going to actually trace out the inner loop because the inner loop isn't part of the boundary of the area we're looking for yet, right? If we're going to do the entire shape. So the blue curve, the top half of the outer loop, starts at theta equals, well, we found that earlier, right? We found that in the last problem. We found that that was theta equals pi over 3. That's when we cross over from negative r values to positive r values. We set r equal to 0 and solve for theta. And it should be pretty clear that then theta continues to increase up to pi over 2, up to all the way to theta equals pi. And then with the red curve, it picks up at theta equals pi. It goes all the way to, you guessed it, theta equals 5 pi over 3. Okay, this is not the same thing as negative pi over 3. They are coterminal, but they are not the same thing. They are not interchangeable. Be careful. Okay, so why am I breaking these up into curves? Because it's symmetric, and I think it's easier to do half of the curve and then double the answer. Unfortunately, we don't have a 0 for any of these theta values, so we're gonna have to deal with non-zero values. So we'll just suck it up. So we know that our area formula is gonna give us 1/2 times the integral from the beginning to the end. I'm just going to do the blue part, so that's going to be from pi over 3 to pi, because I think that pi is a pretty easy angle to work with, probably easier than 5 pi over 3. And we're going to do r squared, which is, well, I already have it right here, ready to integrate. So I'll just copy that part down instead of starting from scratch again. No need to reinvent the wheel. All right, and that's going to be the area bounded by the blue curve and the horizontal axis there. And then because we want the bottom half as well, we'll go ahead and multiply that by 2. Again, for those of my color coding peeps out there, the blue is that integral that I wrote in blue. And then I'm going to double that so I can also get the red, which is the part that is a mirror image of the blue. And then we'll get the total area. What am I doing here? I shouldn't leave out this because we're completely ignoring that inner curve. Yeah. And also here. This is going to give us the entire area bounded by that outer loop, including the stuff in the inner loop. Alrighty, cool. So once again, the 2 and the 1/2 cancel out. That's pretty common. We're going to integrate this exactly the same way. We're going to get the 3, it's already right here, 3 theta minus 4 sine of theta plus sine of 2 theta. And we're going to evaluate that at pi and at pi over 3 and subtract the results. So we've got 3 pi minus 4 times the sine of pi plus the sine of 2 pi minus 3 times pi over 3 minus 4 times the sine of pi over 3 plus sine of 2 pi over 3. All right, so that's going to give us, let's see, this is 3 pi minus 0 plus 0. And then minus, what does all this work out to be? I feel like we did this recently, didn't we? This is pi minus, isn't this just going to be 3 root 3 over 3? Or over 2, rather? Isn't that what we just figured out up here? Yeah, that's all the same stuff, right? All right, so the area bounded by the outer loop is 3 pi minus pi, which is 2 pi, and then minus a negative, so plus 3 root 3 over 2. Now, that's not our answer because it doesn't say find the complete area bounded by the outer loop. Sometimes we'll be asking that, and in that case, we'd be done. But if we want the area bounded by the outer loop but not by the inner loop, we have to subtract out the stuff we found using green up here. So I'll go ahead and shade that in green. And that stuff right there we have to subtract out. So we're going to do blue slash red minus green. All right, so that's the total is 2 pi plus 3 root 3 over 2. That's the total. Minus the inner loop. Could have sworn I changed that to green. Minus that area which was pi minus 3 root 3 over 2. That's what we found in the last example. So that's going to end up being 2 pi minus 1 pi is 1 pi. And 3 root 3 over 2 minus a negative or plus 3 root 3 over 2 is going to be positive 3 root 3. And that is the rest of the area bounded by the curve. Not all of it, not the part that's in the inner loop, but all the other stuff. The part that's in the bigger loop, but outside of the smaller loop. So again, this is the total bounded region. This is the inner loop, and this is in the outer, but out of the inner. I'm sure that was very illuminating. Illuminative? It's time for me to stop this video.